Okay, today we're going to talk about measurement and problem solving. So what we're going to do is discuss how and why we measure things. We're also going to talk about the SI units of length, mass, and time, more about the metric system. We'll also talk about unit analysis, unit conversions, significant figures, and problem solving. So the reason that we measure and how we measure is dependent upon the fact that physics attempts to describe nature in an objective way through measurement. Measurements are expressed in units. Officially accepted units are called standard units. Major systems of units, there's really two: the metric system and then the British system, which is used in the US but ironically is no longer used by the British. Pretty much only the US uses the British system. Everybody else uses the metric system. And so length, mass, and time are the fundamental quantities. Combinations of them will form all units that we will use all the way up through chapter 14. In this text, we will be using the SI system of units, which is based on the metric system. So the SI unit of length is really the meter. The original definition is on the left, and the more modern one is on the right. So the original definition basically measured the distance from the equator to the North Pole as being 10 million meters. But now we measure it by considering the distance that the light travels in 1 over, well, basically the speed of light in a vacuum. And so they're a little off, the old way and the new way, but the new way is more accurate. We use lasers and stuff like that. The SI unit of mass is the kilogram. Originally, the kilogram was the mass of 0.10 meters cubed of water, and now the standard kilogram is basically a platinum iridium cylinder kept at the French Bureau of Weights and Measures. The SI unit of time is 1 second. Now, a second is defined as a certain number of oscillations in a particular atom. That's pretty much it. We used to, the old way is that there are 24 hours a day, 60 minutes represented 1 hour, and then if you took the hour and broke it up into minutes, and then the minutes were also broken up into 60 seconds. But now we measure it a little bit differently. In addition to length, mass, and time, there are base units in the SI system, which include electric current, temperature, amount of substance, and luminosity intensity. These 7 units are believed to be all that is necessary, really, to describe all phenomenon in nature. So we have length, mass, and time. Amps are a way to measure electric current, which is like the flow of electricity. Kelvin is temperature, which is a type of energy transfer that we can measure. Mole is the amount of substance. Usually a mole represents like a number of molecules. And candle is like luminous intensity, or like how bright something is. Sometimes that last one's pronounced candles, sort of. It depends on which textbook you use. So the British system is primarily only used in the US. As I mentioned before, the British system is no longer used by the British. And so the basic units are foot, the pound, which is really a measurement of force, not mass, and the second. However, the SI system is pretty much the only system used outside of the US, and it makes sense for us to kind of become familiar with it because all scientific research, whether it's done in the US or outside of the US, it pretty much uses the SI system. Although engineers in the US do use the British system, so you probably, if you're going to be an engineer, should learn to convert from the British to SI and backwards. In the metric system, the reason that they like the metric system is that the units are the same type of quantity, in other words, length or time, and then they differ by factors of 10, or sometimes I'll say magnitude or orders of magnitude, but it's really just a factor of 10, 10 raised to the first power, second power, third power, and so on and so forth. So here are some common prefixes. And so we would just attach these prefixes to, whether it be length, we would attach it to meters. If it was time, we would attach it to seconds. If it was mass, we would attach it to kilograms, so on and so forth. So tera represents 10 to the 12th, and that's just basically 1 followed by 12 zeros. Giga represents 10 to the 9th, 1 followed by 9 zeros. Mega really represents a million, but it's 10 to the 6th, or 1 followed by 6 zeros. Kilo is 10 to the 3rd. Hecto is 10 squared. Deca is just 10. Deci is 10 to the negative 1, which is really like a decimal. And then centi is 10 to the negative. Milli is 10 to the negative 3. Micro is 10 to the negative 6. Nanotechnology, we usually measure in nanometers, which is 10 to the negative 9. Pretty small. Sometimes with lasers and things of that nature, we have a tendency to use picoseconds because lasers are fast. And so that would be 10 to the negative 12, and I don't need to read them all to you, but those are it. So the basic unit of volume in the SI system is the cubic meter. However, it's really kind of big when you think about it, a meter by a meter by a meter. That's a lot. And so for most things, we don't consume or use that much volume for anything, although that is the standard. However, but remember, a kilogram is equal to, well, technically 1 liter. So 1 liter is something that we use too, and it's really just the weight of 1 kilogram of water, or the volume that the mass of 1 kilogram of water takes up. Pretty cool. So then a powerful way to check your calculations is to use what we call unit analysis. We'll talk about this a little bit more, but basically what we do is if we're measuring a length over time, then our unit should be meters per second. And so like velocity right here, if you take a look at this, velocity is meters per second, which is the length, right? So this is the length, right, over time. Okay, and so if I'm measuring some sort of length over time, then my units should be meters per second. It gets a little more complicated than that as we move forward. What this would look like is, here is a kinematic equation for velocity, and basically I'll read it to you. The final velocity is equal to the initial velocity plus the acceleration times time. And so velocity is meters per second, and then the initial velocity right here would be, again, meters per second. Now acceleration is meters per second squared, and then we're multiplying that by a time, which is seconds. Notice that the seconds will cancel on that last term, so we should have a meters per second, which should equal some unit of meters per second plus another unit of meters per second. Therefore, the equation is dimensionally correct. So sometimes when we go to do our homework, what we'll do is we were not quite sure which equation to use. And so a real quick tip, if you want to use an equation to calculate something and you know that you're calculating a velocity, if you do all the work and your units are not meters per second, then you probably used the wrong equation, or you made a mistake somewhere mathematically. So a conversion factor basically lets us just it permits us to convert from one unit to the next. For example, if we're asked to make a calculation and we're given that a measurement is 12 feet, but we want our answer in yards, we can convert that by simply taking the ratio of feet per yard. And so basically, remember that 1 yard is equal to 3 feet. We could write that as 1 over 3, right? Where this is 3 feet, which is what we have here. And so basically 1 yard is equal or compared to 3 feet. We could also say 3 feet per 1 yard. Okay, now we're going to choose the second option because the second option allows us to cancel our feet, the units of measure, leaving us with the unit we desire, which is yards. And so basically we have 12 times 1, which is 12, divided by 3, which gives us 4, and then our unit of measure, or dimensional analysis, is in yards, which is what we would probably want in this case. And so that's basically it. So a lot of times what you would do, for example, there are 5,280 feet in 1 mile. So I could write it this way, or I could flip it and write it the other way. It just depends on if I want to go from feet to miles or miles to feet. So significant figures is another thing that we talk about when it comes to measurements. We can measure things very precisely, and we'll talk a little bit more about this later on, but there's accuracy and precision. And basically, we don't want to round things too short because we don't have an accurate description of what we're measuring, and we don't want to assume more digits than necessary. So we refer to things as significant figures. In other words, how many numbers do we consider to be important? Do I need to know 1,233.777892 meters, or could I just know 1,000 meters? It really depends on the application. But the calculations that we use may contain two types of numbers: exact numbers and measured numbers. Exact numbers are part of definition, like 2 would be in like this formula: the diameter of a circle is equal to 2 times r, the radius. Well, that 2 is never going to change, and we know it's 2 because it's a mathematical equation. But measured numbers are just that. For example, we might measure the radius of the circle to be 10.3 centimeters, but that measurement is not exact. The way that we read the ruler might not be quite accurate. In other words, it could be 0.31, it could be 0.29, just depending on how we hold the ruler up to the thing that we're measuring. So there's a degree of certainty as to how accurate and precise our measurement is. I would never say, if the ruler only had centimeters, I really couldn't say it was 0.3. I could guess that, but I wouldn't have a high degree of certainty. So when dealing with measured numbers, it is useful to consider the number of significant figures. Significant figures in any measurement are the digits that are known with certainty, plus 1 digit of uncertainty. It's easy to create answers that may have many digits that are not significant in a calculator. Let me give you an example of this. 1 divided by 3, or 1/3 in a calculator, will show as 0.3 repeating. But if we just cut a piece of pie in 3 pieces, how well do we really know that each one is actually 1/3 of the whole? That's the challenge. So significant figures in calculations, there's a couple of rules. And this is based on whether we add and subtract or whether we multiply and divide. When we multiply and divide quantities, leave as many significant figures in the answer as there are in the quantity with the least number of significant figures. When adding or subtracting quantities, leave the same number of decimal places, rounded, in the answer as there are in the quantities with at least one number of decimal places. So, lastly, and we'll do some more examples of the significant figures, but I want to just kind of give you an overview of measurements and what we're going to do. In physics, we measure a lot of things. We have mathematical equations that help us to make predictions of behavior and natural phenomenon. But sometimes we want to apply those models, those mathematical models, or sometimes the concepts attached to models. Or if we want to create a model, we need to observe a certain phenomenon, and sometimes it's not always easy. So we might want to use a problem-solving approach. This is kind of like the scientific method. We always refer to the scientific method as the way that we do science. But as you get older and you do more advanced scientific research, the scientific method doesn't always look the same. And so a problem-solving method can not only be used for scientific research, but when we do our problems out of the textbook, we're going to be solving these different problems. And so the first thing we would do is read the problem carefully and analyze it. Now, I would point out that you don't always read the problem only one time. In other words, you might read the problem, take some notes, try a few things, and then reread the problem. So step one, we're going to do a lot, multiple times in some cases for one homework problem. And that's a good thing to do. Two, when appropriate, actually, you know what, I'm going to cross that out. We should do this all the time, right? So the textbook says when appropriate. Whoops, sorry, I hit the wrong button. It says when appropriate, but I'm going to say all the time, right? Now they're saying like if you have a simple problem that you could plug in an equation, you don't need to draw a diagram. But it's a physics class. You're going to always need to draw a picture or a diagram of some sort. Step three, write down the given data, what is to be found, and make unit conversions if necessary. Some of your homework problems are going to give you the answers in feet, or give you some data in feet, and they'll want your final answer in meters, so you'll have to convert those. Number four, determine which principles are applicable. If the question asks you to find a velocity, you wouldn't use an equation for force. Not necessarily, but then again, you may. It really depends on the situation. Sometimes you'll have an equation that will fit the question exactly the way that you want to answer it based on the information that they give you. And sometimes you got to use two equations and work backwards to get the answer. Number five says perform calculations with the given data. Don't make up data. Look at the data that they've given you and go from there. There's a habit of picking out an equation that you think would work, and it may not work for the data that you have. So just remember, for the same number of unknown variables, that's how many equations you're going to need to use to solve your problems in most cases. Consider whether the results are reasonable. If I'm given a problem where it says that I'm going to have a 5 kilogram weight and it's going to be accelerated at 2 meters per second, and I do all my calculations and I get there are 1 million newtons of force, that doesn't seem reasonable. And so we always want to double check and think, is this answer reasonable? Let's just kind of go through this little chart or example and apply the problem-solving method and see how it might work based on some of the examples that we might run into in the textbook. So let me give you an example, primarily mathematical in nature, and so we would think through the solution. And so sometimes we'll get a problem where they'll give you 3 of the 4 variables, and you can find an equation that has 4 variables, but you have the data for 3. Now what that means is you can plug in the numbers for those 3 variables and then solve for the 4th. An integrated example is conceptual, multiple choice, and then a mathematical follow-up. So sometimes our problems in the textbook will ask you to consider different items or conceptual problems. For example, in 2-dimensional projectile motion, when an object reaches its maximum height, at that instant in time, the velocity in the y direction is 0. That's a concept. But then there's a quantitative reasoning and solution. We may need to use that concept to solve a mathematical problem or equation. Conceptual problems are really easy. Usually just kind of think about the concepts that have been presented in class or in your textbook. Although sometimes we can use some simple math to kind of deduce or justify the reasoning behind our answers. So usually that would be a simple conceptual answer, and then we have to explain why it would work. So quick review of measurements. Basically the SI units are length, mass, and time, and those are going to be meter, kilogram, and second. A liter is actually 1,000 centimeters squared. 1 liter of water has a mass of 1 kilogram. I think earlier I said volume. That was a mistake. I should have said mass. I think I corrected myself. But what you see on the screen is correct. Unit analysis may be used to verify answers to problems. So if your textbook asks you to find the force that's being applied, and you go through and you crank all your work out and you don't get newtons, then you made a mistake somewhere, right? Significant figures. I guess if I were to kind of summarize why we would use significant figures, it's just because of the digits known with certainty plus 1. And yeah, that's a great way to explain it, right? The word significant kind of says it all, okay? Lastly, let's just real quick review the problem solving procedure. This works great not only for physics problems, but any type of math problem. Basically, we want to do step 1, which is read the problem carefully and analyze it. Step 2, which is, when appropriate, draw a diagram. Step 3, write down the given data and what is to be found. And sometimes we'll need to make some unit conversions at that point. It's a lot easier to do it in the beginning, trust me. Step 4, determine which principles are applicable. Step 5, perform calculations with the given data. Step 6, consider if the results are reasonable.